Hi everyone, welcome to Grade Up. In our previous lecture we have seen basics of graph, we have seen some special graph and learn about their properties. In this lecture we will be learning about connectivity, connected graph, disconnected graph, complement of a graph, what is cut vertex, cut edge, all these kind of things we will be covering in this graph. So let's get started. First we will be learning what is degree sequence. Before that you must know what is degree. What is degree? The in a undirected graph. What is degree? Number of edges incident on that vertex. So degree of that vertex is number of edges incident on that vertex. And what is degree sequence? Degree sequence. The degree sequence of a graph is the sequence of the vertices in non-increasing order. Sequence of vertices in non-increasing order. So for example, we have to given the degree sequence of this graph. How can we give it? We just write the degree of each vertex such that in non-increasing order. But this is a cyclic graph, C6. Here every vertex having same degree, which is 2. So how we write it? 2, 2, 2, 2, 2, 2. So in this way we write it 1, 2, 3, 4, 5, 6. Okay. So this is the degree sequence of this graph, and we can. So this is just like that. Now there is Havel-Hakimi result. There is Havel-Hakimi result, and what this result says, suppose this is the degree sequence of a graph, and we need to say whether it is a valid degree sequence of a graph or not. Sometime happen that it is not a degree sequence of any graph. That may be happen, and the Havel-Hakimi result will try to figure out whether a degree sequence is a sequence of a simple graph. Simple graph, remember it, okay? Simple graph. Now I try to identify without even, if you suppose you don't know Havel-Hakimi result and I asked you whether this is a correct degree sequence of a simple graph, how can you answer it? So I told you in previous lecture one very important result, that is handshaking lemma. Try to use it and try to say whether it is a valid sequence or not. So what's handshaking lemma says? Handshaking lemma says that sum of degree of all vertices should be even. So if you take the sum of these number, this is even number obviously we get, and this is 2 odd number, that is will be a even number, this is even number, and we get an 1 odd number. So the sum of these degree will be odd. So according to handshaking lemma, that is not possible. So this is not a degree sequence of any graph. Now for this sequence we will try to use the Havel-Hakimi results, and I will tell you how to use it. For the definition you can refer the book, but I will tell you how to use that. Okay, suppose this is, in this graph we have to use it. So I am writing here this, I am writing here 5, 4, 3, 3, 3, 2, 2, 1, 1. Okay, now how to do it? First this is, see this is 5. So what you do, mark 5 point, 1, 2, 3, 4, 5, and you will decrement all of these. You will decrement all of this by 1. You will decrement all of this by 1. So decrement it and remove it. Remove that. So it will be 3, 2. This will also become 2. This will also become 2. This will become 1. This will become 1. But what in degree sequence, I can write it 1 here. Okay, let's write it 1 here, then 2, and then this is 1, 1. Now you need to, now you see that 2 is coming after 1. That should not be happen. Always they are in the increasing order. So make it 3, 2, 2, 2. This 2 come here, 1, 1, and 1. Now what will you do? Now you will do for this 3. How will you do? 1, 2, 3. Okay. And now see this 2 will come. So I am writing it ahead. Why I am writing ahead? Because I should not do again this step. So I am writing it ahead. Okay, now I write it. Now this will become 1, 1, 1, and this 3, 1 are also there. Now this is for 2. So how can I do it this? And also remove that. Okay, we are doing this. You make it 1, and this is the 2. We remove that. Okay, that is fine. Now for this we remove it and we do it for this, and all this one should come ahead because they will become 0. They should come back. I am writing all this one first. 1, 1, 1, 1, 1, and it will 0, 0. Now I am coming at here, now I should do that. You can continue, but the important interesting thing that at any point during this procedure, when you realize that this can be we can draw this simple graph, you can stop. How can I draw this simple graph? This is 6 vertices, okay. If I draw like this, it is possible, because this vertex will be having 1 degree, 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 and this is 0 and this 0. So I can stop at this point and I can say that, what I can say that yes, simple graph can be possible, or you can continue that procedure. So right now I am here continuing that procedure, so I mark it as 1, so I remove it and decrement it by 1 and it will become 0. So I am placing it at the back, so I don't need to do rearranging of this, so that 1 comma 1 will come and we get 3 zeros. Okay, now this is 1 and we need to remove it and we need to decrement it, we get 4 zeros. So in Havel-Hakimi, when you get all 0 like this, then there exists a simple graph. When you get all 0 like this, then there exists a simple graph. If you don't get like this, then there does not exist any simple graph. Okay, so you can try for this one and see whether it will be or not. But before applying Havel-Hakimi theorem, I always recommend that you should see whether the sum of degrees is even or not. If it is not even, you can directly say it is not the degree sequence of any simple graph. Okay, so see a question based on what we have learned Havel-Hakimi. So this is the same question based on that. So these are the degree sequence we are given, and the question is asking cannot be the degree sequence of any graph, cannot be the degree sequence of any graph, and it is talking about simple graph, it is talking about simple graph. So we need to find out. So I told you how to apply the Havel-Hakimi, and we will do this for this one also. So how we will do it? We try to remove 1, 2, 3, 4, 5, 6, 7. Why I write this 7? Because it is 7. Here it is 7. That is why I am writing this as 7. Now decrement all of this by 1, and what we will get? 5, 4, 3, 3, 2, 1 and 0. Okay, we will get this. Now what I should do? Now I will mark 1, 2, 3, 4, 5 and I will do it again. So it will become 3, 2, 2, 1 and 0 and 0. Okay, now I will do it one more time, then it will become 1, 1 and 0 and 0, and I can stop here because I know that there exists a graph like this. How it is exist? This vertex and this. So we have 2 vertex with 0 degrees and 2 vertex with 1 degree. So I can stop it, or you can continue and get all zeros, and when you get all 0 you can say that yes, this graph exists, but the question is asking cannot be the degree sequence. Okay, so we need to find it. Now see in this what we will get. So here how many are there? 1, 2, 3, 4, 5, 6. Okay, we need to do it. So how will we do it? 5, 5, 5, and this will become 2, 2, 2, 2. Now see, this will become 1, but I am not writing this as first because we need to do arrange, and in GATE examination there is very shortage of time. That is why I am writing first here 2, this 2 and then 1. So rearranging and both are doing at the same time. Now we need to 1, 2, 3, 4, 5 and I am removing it. What we will get? We will get 4, 4, then this will become 1, 1, 1 and 1. Okay, now I am again doing 1, 2, 3, 4. You must understand the procedure I am doing. Whatever the number written is here, I mark these 4 and decrementing them 1 and writing them, and then we are arranging them and then doing the same procedure again. And when till what time we need to do? Till we get all zeros. Okay, when we get all 0, we can say that there exists a simple graph for this degree sequence. If we didn't get all 0, we cannot say there exists a simple graph. Okay, and I also just check whether their degree sum is even or odd. I didn't check it here, but you can check it now also or later. So if I check it, these two make evens, okay, and these two makes even. So this is gonna be even, and this all here, these two makes even, which are the odd ones. So it is gonna be even sum, okay. And if you see here, this is odd, okay, and this is odd. 2 odd and 2 odd makes even. That is why this sum is also gonna be even. How I am doing, understand it. I am just trying how many odds are there. If the number of odds are even, then obviously we are going to get the sum of degree sequence as even. If you see at here, how many odds are there? 1 odd, 2 odd, so this make even, and 1 and 2, so this again make even. So all of these having an even sum. When you sum all the degrees, you will get the even sum. So there are chances that they may be the degree sequence of a simple graph, but we can't say whether they are or not. For that we need to apply this Havel-Hakimi theorem, and I am doing for this, and I come to that point. Okay, so here I will decrement it by one more time, and it will become this one I am writing first because they become all 0. And now I am doing, we need to do 3, but you see that we can't do for 3 vertex because it is already gone 0, it will become negative. So for this sequence there does not exist any simple graph. For this sequence there does not exist any simple graph. Similarly, try for this one, and you will find that there exists. And for this one, we can see it here, 1 2 3 4 5 6 7. Here we got 7, but it is first number is 8. First number is 8. So obviously there does not exist any simple graph for that. Okay, so do 2-3 example. I think 2-3 example will be fine to understand that, and after you understand that, then move ahead. Okay, so the question was asking about cannot be the degree sequence. Which one are not there? Second and fourth. So right option will be fourth. The second and fourth cannot be the degree sequence of any graph, simple graph. Now what is connected graph? So what is connected graph? When in a graph, in between two vertices, when there is a path, then you can say that it is a connected graph. Every two vertices, pick any two vertices and try to find there exists any path. What will be the path? Suppose this and this, and these are the edges. Okay, these are the edges. Now I am picking this one and this one. What will be the path? I can either go by this way, or I can either go by this way. So this will be a path. Okay, or I can even go this way. So this is path. This is known as path. Okay, or you can go like this. So there is path between every two vertices. What is disconnected graph? When you find you find two pair. When you find two vertices such that there is no path between them, then you can say that this graph is disconnected graph. When you say a graph is disconnected, suppose you find two vertices such that there is no path between them, then you can say this is a disconnected graph. This is a disconnected graph. Understand this, because we are going to use this again and again. To prove some statement, we are going to use this thing that when a graph is disconnected, there are two vertices such that there is no path between them. And what is connected component? So connected component C should be the subgraph of G. Should be subgraph of G. Okay, C should be connected graph, and there is no super graph of C which is connected. This is important. Okay, there should not be super graph of C which is connected. I am taking an example. So this is my graph, this is graph, and I am asking you how many connected components are there. This is one connected component, and this is another connected component. If I ask you, so there are two connected components. In this graph there is two connected components. What if I say this is a connected component? No, this is not a connect, only this, one vertex, two vertex and three vertex. If I say this is a connected component, this is wrong, because there exists a super graph such that this super graph is a connected component. So that is why there should not be super graph of C which is connected. Okay, and this is important. So in this graph there are two connected components. When a graph is connected, how many connected component will be there? Answer it. Only one connected component will be there. Now we'll see complement of a graph. What do you mean by complement of a graph? So we represent complement like this. Okay, where V complement is equal to V. This is equal to V. Okay, but E is different. E complement is different. How it is different? It is different because here, suppose there are n vertices. There are n vertices. So you need to find the number of edges in complete graph, and then then do not add any those edges which are present in this G, okay, but add all those edges that are not present in G. For example, suppose we have a graph like this, okay, we have a graph like this. So this is G, this is G. Now what it is asking, this is G. Now in G complement what will be happen? We know that this is a 4 vertices, we can draw, this will be K4, complete graph with 4 vertices. Now see what are the edges are present in G, this present, so we do not add this and this. These 3 I will not add, but these 3 I will add. So in G complement what will be happening? We get like this, okay, we will get like this, okay. So G complement is this, understand it? It is easy, okay. Now do a question, a simple graph with 10 vertices and 25 edges, then number of edges in its complement. So graph having 10 vertices and 25 edges, you need to find the number of edges in its complement. So how will you do it? We have these definitions and try to do yourself, it's easy. So how to find that how many edges will be there? So to that, how the number of edges, what we will do, I will find first the number of edges in complete graph with 10 vertices, okay. So how many edges, and then subtract it, so that should be our answer. So how many edges with 10 vertices will be there? 10 into 9 by me 2 minus me 25. If this will be 5, 45 minus 25 is equal to me 20. And how I will get this? Because the number of edges in a complete graph with n vertices is n into me n minus 1 by me 2. We have proved this by two way. In two way I prove this statement, okay. So whenever you say something in graph through it, try to figure out some intuitive proof of it, because you will not remember it and you will not use it if you don't get any kind of proof, okay. So try to remember it. Cut vertex and cut edges. So what is cut vertex? Cut vertex, when you remove a vertex from a graph, if that by removing that vertex the graph will become disconnected, then this vertex is called cut vertex. And what is cut edges? Similarly, when you remove an edge from the graph and by removing that edge the graph will become disconnected, then it is called cut edge, okay. So these two are the definition of cut vertex and cut edges. Now I am giving you a graph and I am asking you find the cut vertex in this graph and cut edges, okay. So pause it and without saying answer try to find it. So how to do it? Simple, very simple. First we will finding cut vertex. So if I remove A, then this all will be removed, completely removed, and then our G will be only this portion here where I am marking my A, and it is connected, so A cannot be a cut vertex. If I remove B, what will happen? That A will be remain here and this edge gone remove, this edge gone remove, and this edge gone remove. When we remove a vertex, we also remove its associated edges, okay. So this vertex will be there and this is the another graph, another component. So one component, two component, graph will become disconnected. So B is a cut vertex. Similarly, if I remove C, what will happen? I remove this. So this component one will become and another component will be this. So C is also a cut vertex. What if I remove D? I remove these two vertex edges and D. Even then the graph is connected. So D is not a cut vertex. Try it with E. When I remove it E, this four edges will removed and this will be the another one component and another component will be this one. So obviously I cannot remove, okay, it make the disconnected graph. So yes, this is also a cut vertex. If you see remove H, then these two will gone, but this is gone, completely gone, and our graph will only this, and our graph is still connected. So H is not a cut vertex. Similarly, removing G does not make the graph cut vertex, and removing F does not make the increasing the number of component, okay. When you remove a vertex, if it increases the number of component, then it will be known as cut vertex. So B, C are the cut vertex. And what are the cut edges? If you remove CE, there will be two components. Okay, so CE will be the one. And if you remove this edge, what will happen? A will remain here. When you remove an edge, the associated vertex will not be removed. Okay, it should not be like that. But when you remove a vertex, associated edges also get removed. Okay, so A will be here and all the remaining, this graph will be here. So yes, this edge AB is a cut edge. If you try, if in this, I am removing all these marks. Okay, if you in this if you try to remove BD, still there is a, this is connected. If you try to remove DC, still it is connected. If you try to remove BC, still it is connected. Why? Because it is connected, because there is a cycle. That is why it is connected. Whenever there is a cycle, to reach between every two pair of vertices, there are two ways to reach it. For example, B and D. I want to reach from B and D, and there is a cycle. I know there is always a two way. That is very simple to see how one way is directly going there and second way directly other way around, opposite side of cycle. Okay, so there are two ways always. So removing a vertex, removing an edge from a cycle does not make a graph disconnected. So I can see all these edges are in cycle, so removing any edge does not make a graph disconnected. So don't check for them. Okay, so only AB and C are the cut edges. What is vertex and edge connectivity number? So vertex connectivity number, minimum number of vertices required to disconnect the graph. Okay, so sometimes it happens that with removing a one vertex we cannot make a graph disconnected. For example, I will show you this graph. Try to remove a vertex and you will see that no, we cannot make this as disconnected graph. Okay, so if you remove this vertex, you will not make it, because there are, okay, you cannot make it by removing one vertex here. You need to remove this also, and then only one vertex will be remaining, and that is known as, you can't do much further. So there are, the vertex connectivity number for this graph will be 2. Okay, and what is edge connectivity number? Minimum number of edges. Here it is minimum number of vertices, here minimum number of edges to disconnect the graph or increase the connected component. So these two are, sometimes question are framed based on that. Okay, see this question. This question is really interesting. Non-empty graph, and we need to identify whether these two statements are true or not. So in graph theory, whenever you find a statement, try to find its intuitive proof, because that is the only way you can remember it, that theorem, and you will use it. See S1. If G is disconnected, then G complement is connected. So this is a statement, and try to prove it. You need to prove it. Okay, so try to prove it, and I am also doing. So I am going to prove it by proof by contradiction. So it means that it is saying G is disconnected, then G complement is connected. And when I am going to prove by contradiction, then I am assuming that S1 is false. I am assuming that S1 is false. So this statement will become, if G is disconnected, then G complement is also disconnected. So when G complement is disconnected, that means there are two pair of vertices. I am representing by like that. So this is one vertex and this is vertex, such that there is no path between these two vertex in G complement. Okay, in G complement there will be no path between these two vertices. But if in G complement there is no path, then according to definition in G, there should be path between these two. Okay, there should be path between these two. But see, G is also disconnected. So there must be some connected component. Okay, there must be some connected component, so that G is not, these two are not connected to that connected component. I am naming them. This is Ram, this is Sita, and this is Lakshman. Okay, so now what I am saying that G, this is G, okay, this is G. G in G, there should also be a connected component, so that these two are not connected, because G is also disconnected graph. So so Lakshman and other member of Lakshman are like that. Okay, now what will, according to the definition of G and G complement, when there is no edge between these two, then in G complement there should be an edge. That is what it is mean by G complement. Okay, so here in Lakshman, with Lakshman, here with Lakshman there will be a path, and there will be a path between Ram and Lakshman and Sita and Lakshman, but there is no path. Now see, I started by saying that G complement is disconnected, and I say that there are two such pair, Ram and Sita, which are disconnected, but I am seeing that they are connected. So my assumption is wrong. It is contradicting with my assumption that S1 is false. My assumption was that S1 is false, but now it is contradicting with my statement, because I see there is a path between Ram and Sita, which is through Lakshman. So my assumption is wrong, and this statement is true. This statement is true. Now see second statement, S2. If G is connected, then G complement is disconnected. If G is connected, then G complement is disconnected. So we need to try to prove it. Try to prove it. You yourself do it. I can give you a hint. You can prove this statement by a counter example. By counter example means show that G is connected and G complement is connected. Try to find one such example such that G is connected and G complement is connected. Once you do it, then this statement become false. Okay, I am also doing here. Suppose this is G, and now I am doing its, this is with 4 vertex, this is G, and when I draw its complement, it will be like this. It will be like this. See, both are connected. Both are connected. So this statement is false. This statement is false. This statement is false. So whenever you see any statement in graph theory, if you try to find its intuitive proof or a detailed proof, then you will always feel confident in graph theory. By seeing a statement, you will not hesitate, and you will try to do more and more example on graph theory. And once you do lots of example, you will become really good in graph theory. And in I already told you before that in IITs from graph theory, they ask in interviews, they'll ask lot of questions. It also comes in GATE examination, but in interview also they ask lot of questions. They give a statement and they want you to prove it, because proving something really requires intuition and many other things. Okay, see this question that is asked in GATE 2014. G is a forest with k vertices. So what is a forest? When you have lots of trees, then it will become forest with n vertices and k connected component. So there are n vertices and there are k connected component, and we need to find how many edges G have, and these are the options. So how can we find it? There are how many component? K component. So we need to find it. So how to do it? Suppose this is one component, this is second component, so on. This is kth component. So I am writing C1 component, C2 component, and this is CK component. Okay, and what if I do the, suppose C1 representing the number of vertices in this complement, this also. So when I do the summation of C1 plus C2 plus C3 so on plus CK, then this is equal to man. C1 representing the number of vertices in first component, C2 representing number of vertices in second component. So this is a statement. Okay, now every one of this is a tree. How they are tree? Because in forest everyone is, this is tree, and group of trees is known as forest. Okay, so this will be a tree. So you must know that when a tree having n vertices, then how many edges it will have? N minus 1 edges. If there is more than n minus 1 edges, then there will be a cycle, and in tree there will be not a cycle. Okay, so it is always true. Whenever in a tree there are n vertices, then there will be n minus 1 edges. In a tree, that is always true. So for this component, how many edges are there? C1 minus 1. Here C2 minus 1. and so on. I am counting the ages. So we need to do the summation to find all the ages in these. Okay, so I am doing it, and this will be ck minus 1. So this is the number of ages. This is the number of ages in this forest. So now what it will be, c1 plus c2. I am just taking this and this and this and removing that, plus c3 and so on, ck. And how many these one are there? How many component are there? K component. So these one are there, 1 1 1 1 1 k times, and when you do the sum of this one, it will be k. And what is this? This is equal to n. I already written it. Okay, so what it will become? N minus k. So answer is C option. Answer is C option. So that's all for today. Try to do lot of practice, and whenever you found a statement in graph theory, don't afraid of it, and try to find some intuitive proof or a detailed proof if it's required. Most of the time you will get an intuitive proof of that statement, and that will be very fine. Okay, so keep practicing. Thank you.